and welcome back to another tutorial. Today I would like to show you what might happen if you don't fully constrain a reference profile and how to fix it. For this, I have here an example with some HR AMS data, and I know that I have a traffic factor in this data set, but it's not very clean, and therefore I would like to constrain it with a reference profile. So I go here through the orange panel, I set a seed value, but what I see now is that some variables don't have a seed value and that this button here is still yellow and has not turned green yet. The same goes for the A value. I only have an A value where I actually have a seed value. This is because my reference profile does not contain exactly the same variables as my PMF input. We can see this here. Here I have my variable list of my PMF input, and here you can see the variables of the reference profile, and there are a lot of variables that do not exist in the reference profile. The reason for this is that back in the day when the reference profile was recorded, the AMS most likely had a much lower resolution and one was simply not able to fit so many ions back in the days, and therefore they are not present in the reference profile. So when I run PMF with the constraint that I set up with the original HOA profile, this is what my result looks like. Let me pop this for you. If we look now here, I constrained the first factor to be my HOA. Here I have a graph of what I expect my HOA to look like. This does not look like HOA at all. So let's see what happens if we zoom in a little bit. What we can see now is that we have some ions that have this gray bar here. This gray bar is to show you visually what was constrained for the PMF run, and we can see that the ions were actually constrained, and that still kind of resembles the HOA profile here. However, things are dominated by other ions that are not that were not constrained. To show you this in a bit more condensed way, I prepared this graph here, and what you can see here is again the factor 1 from the PMF result with the gray bars, and here the reference profile, and you can see that it actually matches quite well. Don't pay attention to the absolute values because the profile is always renormalized after the PMF analysis, but you can see the constraining works. The problem is that the unconstrained variables are actually just dominating. So what we have to do is to also constrain our ions where we don't have any information about. The way we do this is we go back to our orange panel and first to set a seed value. Now we don't want to set the missing ions to 0. As I said before, that most likely the reason that they're not present in the reference spectra is not that they're not there in the traffic factor, but rather that back in the time, those ions were just not measured or could not be fitted. So we know that we don't want to set those variables to 0, but we don't know to which value we want to exactly set them because we don't know which final value they will have in the solution. We just know that we don't want them to overshoot and to dominate the profile. Our solution to this is that you constrain those missing ions with an A value of 1. Having an A value of 1 allows the variable to go down to 0, but also to get double the intensity that it was constrained with. So now for constraining those missing ions. When you import the reference profile through Sophie, Sophie can automatically create a missing ion wave for you. You just go through the yellow panel if you have questions about how to do that, there's a separate tutorial video for that. Here I already have the missing ion wave, and this one I now constrain in addition to the original HOA profile that I have. So here I still keep from vector. As an external vector, I now select the HOA missing ions wave, and I select not all entries, this is very important, but all variables of external vector. Another thing that is very important is those intensities in the missing ion wave are based on the maximum intensity of your reference profile as a fraction thereof. So you don't want to change that value, and therefore you need to select here the non-normalized option. Otherwise, those values will be changed when you constrain them. So we now just click here into write model matrix. And as you can see, now all the empty slots are filled with those with this value for the missing ions, and also here the button turned green. Now we go over to the A value, and here we do it very similar. We select here the exact A value, and then we select again not all model variables but all variables of external vector, so that it only takes into account the ions that are part of the missing ion wave. And then we put here an A value of 1. And as you can see now, also we have A values for each and every variable. Let's run this PMF analysis again, but this time not only constrained with the original HOA reference profile, but also with the missing ion list. If we now look into the solution, let me pop this for you. First of all, we can see that this kind of looks like an HOA profile. We have here the hydrocarbon groups. What you can also see is that now each and every variable has a gray background. So that means that every variable was constrained. What we can also see if we zoom in here a bit, that for some variables, they actually go down to closer to 0, so it's not even trying to push the upper limit of what we gave as a starting seed value. Let's also look at this maybe without the A values to see it a bit more clear. This still looks like a HOA profile. And this is how you can fix a partially constrained profile that is overshooting. Of course, I showed you only the simplest case where you have an exact A value for your reference profile, but of course you can also use this approach with any other option here for the constraint type. Just make sure that you always use an A value of exactly 1 for the missing ions. I hope you learned something new today, and I hope to see you in another tutorial.